Great. Yep. So thanks for coming. This is joint work with Jungwon, Robin, and Ryan. So here's the problem setup. So let's say like an experimentalist has some gates for your brand new quantum computer, and you want to. It's like a gate, and this is like a black box thing that you can apply, but you want to know what it does, or you want to verify that it's doing what you think it's doing. So, we abstract this to the setup of you have some unitary that you're applying, and you don't know z. And what you want is you want to figure out what z is. That is, you want a classical description of z, like a list of entries that give you some estimate, and you want this estimate to be close to z in diamond distance. So we want a epsilon good estimate to our unknown unitary in diamond distance with some probability 2/3 that you can boost if you want. So I realize diamond distance might not be the easiest metric to think about. For unitary channels, this is you can actually instead think about the operator norm distance between the two matrices. So for U and V, two unitaries, I can consider like the difference between U and V and operator norm sort of up to a global phase. And this is going to be the thing that we're going to use for this talk. Okay, so what our results are is, so in fact, if you consider this problem is known as like process tomography. If you consider it for general channels, you have to pay a 1/epsilon squared scaling in the query complexity and the number of times you apply your black box. However, if you restrict to unitary channels, it turns out that you can actually get a 1/epsilon scaling. And what we give is an algorithm that is able to achieve this scaling. And in particular, we are able to learn or estimate this unitary in d²/epsilon queries. And this algorithm has a couple of nice properties. First of all, it only uses one qubit, so there's no space overhead at all. We are just basically applying pretty simple quantum circuits, sort of only on your d-dimensional system. Furthermore, we only use queries to z, so we don't use like the inverse or controlled. We don't need like a controlled version of our black box. And this is, I guess I found this a little bit surprising because usually if you want to get a 1/epsilon scaling, you sort of often need to use these sorts of stronger models, stronger access assumptions. Okay, and furthermore, we prove a lower bound that says that d²/epsilon is tight. So we basically get the right upper bound, we get the right lower bound. So I'm not going to be discussing the lower bound in this talk. I do think it is pretty cool. So yeah, if you need something to do tonight, I recommend our paper. Yeah, so I'm going to be talking just about the algorithm, and hopefully I'll get through the whole thing in this talk. Okay, so the prior work, surprisingly, we are not aware of anybody who's studied this particular problem specifically. The closest work is that of Yang, Renner, and Chirabella. And they solve this problem sort of on the way to solving another problem that they're concerned with, this universal programming problem. And what they do is they show this, they give an algorithm for this unitary estimation problem, where instead of wanting error in diamond distance, they want error in like a weaker metric of entanglement fidelity. This is like the operator version of fidelity. And so if you translate their result to our setting, the diamond distance, you get a d⁵ And furthermore, their algorithm is just applying all of your oracles in parallel. So it has a really big space overhead. Right, so, and the other typical way to solve this problem is using some process tomography technique. This is, I'm going to cover it a little bit more, but basically it's like you prepare a state, you apply your black box, your oracle, and then you measure. And then you do this a bunch of times, and then you use this to get your estimate. And this gives you like a 1/epsilon squared scaling. but it is only using one qubit. And you can try to soup up this process tomography procedure, and this will give you something like d squared log d over epsilon, if you use things like amplitude estimation and things to sort of get this Grover-like speed up. And the issue is that you still really have like some space overhead. And also you're using things that are like quantum linear algebra type techniques, and so you need these controls and inverses. So we sort of get the best of all worlds. Right, so I'm going to talk about the algorithm now. There are two parts. The first is we're going to give a d squared over epsilon squared algorithm, and this is like in sort of this process tomography type regime. So we're going to give a d squared over epsilon squared algorithm. We couldn't find a reference for this, but this is, as far as we know, pretty standard. But I'm still going to talk about it because it's, I think it's interesting. So, and the second step is some bootstrapping algorithm that sort of in a black box way converts any d squared over like poly epsilon algorithm or d squared over any scaling into a d squared over epsilon algorithm. And so this is sort of the main contribution of our work. Okay. So first of all, the d squared over epsilon squared algorithm. So this is generally going to follow how quantum process tomography works, in the sense of, okay, how do I learn this unitary matrix? What I'm going to do is I'm going to learn it column by column. So I'm picking a basis, and say it's like the computational basis 1 through d. And so for a particular basis vector k, I apply my my oracle to it to get the z ket k, and I get a bunch of copies of this. And using these copies, I'm going to run a state tomography algorithm to learn what this state is. And this is going to give me some estimate uk that's sort of like a list of entries, and using this list of entries, I'm just going to sort of collate them into an estimate of the unitary. Now, the state tomography guarantee that you get with d over epsilon squared copies, right? So because we need d squared over epsilon squared copies, so it's d over epsilon squared per column. What we can get is that our output vector is close to the true value, this column, in Euclidean distance and L2 distance, up to some phase that we don't know. And something I'll note is that you can basically conjugate this algorithm. You can sort of apply a random unitary, sort of prepend and postpend your algorithm by this to make this error unbiased. So it's sort of in a random direction. Okay, so what did I say that we were doing? We're taking these columns, and then what we have is that we can estimate it by these estimates that we get from state tomography, and this is multiplied by some phases that we don't know. And what you can show is that these errors, the error between these our estimate and the desired thing is given by the operator norm of the column of estimates. And you can show that because these errors are random, these are random columns, this is bounded by like epsilon. Okay, so all that we need to do now is to estimate these phases. Right, because there's a different phase on each column that we potentially don't know, and we need to fix this. So what we're going to do is we apply the same procedure to two different bases. So we're going to choose the computational basis, and we're going to choose the Fourier basis. So we apply our procedure that I mentioned before on Z and ZF, where F is the discrete Fourier transform. And we get these estimates U and V, which up to these sort of column-wise phases are close to Z and ZF. And you can combine U and V to get you can combine U and V here to then see what the phases are. So you can look at U dagger V, and because this U is close to Z times phi dagger, and so on, you can get that these Z's cancel, and this is a close to your Fourier transform, but your phases are sort of there's a phase per row and per column. And so what you can do is you can basically just like look through here to see what phi 1, phi 2, phi 3, and so on are. And this will give you your approximate phases. And so then this is all that you needed for your problem. You're done. You do only learn this up to a global phase, but we didn't expect. But you have to pay a global. You have to. Your algorithm has to work up to a global phase. So this is fine. Okay. Now I'm going to talk about the d squared over epsilon algorithm. So if you didn't follow what I said before, that's fine. You can zone back in. This is not going to use that. What we are going to show, as I mentioned before, is that if you give me some base tomography algorithm, so this is your favorite algorithm that if I give you some black box oracle to the unitary, it'll give me back some estimate to constant error. Then what I can do is I can apply this for various different choices of my oracle. And what it'll give me is an epsilon good estimate. And the number of queries I use only inflates by a factor of 1 over epsilon. So what I'm doing is I'm taking sort of a weaker algorithm and I'm making it stronger. So if I apply my d squared over epsilon squared algorithm, which I discussed in the previous section, then if I use this to estimate my unitary to constant error, then this requires d squared queries. And so this theorem, this bootstrapping, will give me an algorithm that gets epsilon good estimates with d squared over epsilon queries. And it'll turn out that if your base algorithm only uses 1 qubit, then so does the bootstrapped algorithm. Okay. Now to provide some intuition, we'll consider a warm-up case. So we're going to consider not d dimensions, but 2. We're going to consider a unitary on a qubit. And what it is it takes this form. So it's like 1 and phi. And all that we want to know in order to figure out what this z is all, we just need to figure out what this phi is. And the approach that we can do is a kind of phase estimation. Specifically, it's like a kind of robust phase estimation, if you're familiar with this. What you do is you can run your base tomography algorithm on z to the 2 to the k. So this will give me a constant error estimates to z squared, z to the 4th, and so on. And with these constant error estimates, if I look at what z to the 2 to the k is, it's going to be the diagonal matrix with 1 and then phi to the 2 to the k. Well, all that we need to know is what this phi is. So we can look at the corresponding entry of uk. And this will give me still a constant good estimate of the phi to the 2 to the k's. So I'm taking these, I'm using my base tomography algorithm to get these estimates. And then from these estimates, I'm extracting some estimates of the phases, this phi to the 2 to the k. And if you see, if you sort of think about what's happening, every estimate of every estimate that you get is going to tell you a constant size interval that you know that phi is in, phi squared, phi to the 4th, and so on. So you're getting only constant error estimates to phi squared, phi to the 4th. But if you look at, and what you do is you look at what these intervals will tell you about where phi is. So you sort of pull back and see that, okay, if I know that phi squared is in this one blue interval, then phi must be in one of these 2 blue intervals. And similarly, for phi to the 4th, if it's in this one constant size interval, then it's in these 4 intervals of like 1/4 the size. And using all of these estimates, I can see that I can extract, look at where these intervals overlap and extract an estimate. And the estimate is improving by the factor at which I power up. So if I power up to phi to the k, then my estimate is improved by a factor of 1 over k. And so using this, if I power up all the way to 1 over epsilon, then this will give me an epsilon good estimate. So this is like more or less like learning 1 bit at a time. So you would hope that this sort of approach for the warm-up also works for in general, where your matrix is like not diagonal. So this approach, as I mentioned before, was that you run your base tomography algorithm, and this gives you constant error estimates to your powers of z. And you want to take these estimates and somehow extract an improved estimate of your base oracle, your z. And you can see that what's happening is like if I'm running this on powers, then sort of I'm only incurring an overhead of 1 over epsilon. That's sort of like why this is. We hope this could work. However, this does not work. One easy way to see this is that if your unknown unitary is a reflection, then it has eigenvalues 1 and minus 1. This means its square is the identity. And so if you actually run your algorithm, you're going to just see the identity. So you're not getting any useful information past like the first couple of iterations. What I say is sort of not precisely true. You can sort of estimate the spectrum still, perhaps. But what really is at issue is that you're losing access to the eigenvectors. So whenever I power up, it's somehow like I'm not boosting my estimates of the eigenvectors. And in this extreme case, you lose access to the eigenvectors entirely. So what we are able to show is that this is, in some sense, the only hard case. So if we remain close to the identity, then this approach from the warm-up will actually work. And the main structural lemma that's used here is actually, I guess it's like the only structural lemma, is this statement, which says that if we have u and v, which you can think of as like, let's say z to the k and an estimate to z to the k, if these two are close to the identity, then when I take roots, let's say the kth root, then the distance between the kth root of my estimate and now it's z is going to improve by a factor of p, of I guess k here. So what's happening is that if I know that I'm close to the identity, then if I take roots of, if I have two unitaries and I take their roots, the roots are getting closer and closer together. And this is the condition that you need in order for the warm-up to work. Okay, so this is uses some arguments in like Lie algebras. Okay. So the main idea is that, okay, we want to run our algorithm, but we also want to stay close to the identity. And so the way that we do this is we run our algorithm, like what we power up is not z, but the remainder, like the error of our estimate, right? So if we consider our current estimate, like an estimate at a current iteration, uk, if this is close, then you know that z uk dagger is very small, or it's very close to the identity. And so this, you can power it up. So the idea is that what we do is we look at this remainder, and then we power it up by a factor of 2 to the k in the kth iteration. And then with this estimate of the sort of powered up error, we can power back down and then adjust our estimate to something that's better. Okay, so the analysis, as I mentioned before, you can see that because that we're running it on z to the 1 over epsilon at like the largest, the query complexity is only blowing up by a factor of 1 over epsilon. We're also using the same space complexity because this is the only quantum part. The rest of it you can do on a classical computer. Okay, and there is a bit of analysis that I won't get into, but basically it just follows that you use this lemma, and when you use the lemma and have an inductive invariant, you are done. So this is like the entire proof. Okay, so some final comments. We're also able to recover Yang, Renner, and Chirabella's results for sort of the problems that they're concerned with related to like entanglement fidelity and their application of like storage and retrieval. And as for open questions, we're interested in whether the gate complexity of this approach can be improved. We're also interested, or I'm interested in whether these techniques, this is like a simple idea, but I think it could find use in other problems, other estimation problems. Okay, thanks.
Thank you, Evan, for a nice talk. I have a short question. In the meantime, please feel free to line up for the mic. So you said that in some sense, the only hard instance was the case when you had a reflection.
Mm-hmm.
And of course, in the worst case, you can have like reflections which are like half plus, half minus, so eigenvalues are kind of balanced.
Mm-hmm.
But do you know if your algorithm can be modified in a case when you know that you have a reflection, it's promised it's a reflection, but only has like say k minus 1 eigenvalues? Can you learn that unitary with dk over epsilon uses of unitary only?
Sorry, you said you know that there's only k eigenvalues that aren't one.
Yeah, so it's a reflection. You are promised it's a reflection matrix around
Mm-hmm.
a k-dimensional subspace,
Mm-hmm.
and of course then it's a much lower dimensionality problem than the worst case. So like d square should be possible to replace by dk. Is it plausible in your algorithm or?
Yeah, we did consider this for this like case of like a rank 1 reflection. It's not clear to us whether you can do this just because sort of what we're exploiting is some kind of like some kind of structure, some kind of metric structure on like the group of unitary matrices. And so if you consider these like reflections, you sort of are not able to boost the error, or it's not clear how you boost the error in that sense. So I'm not sure. Yeah.
Thank you.
Thanks for the talk. Can this algorithm be used to test whether Z is unitary if it is not guaranteed?
I think probably testing unitarity is somewhat easier because all you have to do is well, so short answer is yes, you can do it. Like if you're at least like in the simple like error models I'm considering, more or less like your tomography algorithms will start to notice if your matrix, if your states that it's seeing stops becoming pure. Your algorithm will notice that, and so you can detect that and see that. But I think there might be an easier way of, or like at least like with fewer queries of seeing that something's far from unitary. I'm not sure.
Thank you.
Thanks for the nice talk. With the algorithm that you're bootstrapping, did you need that to succeed all of the time, or was it enough for it to succeed with some probability?
Yeah, great question. I push that under the rug. As long as you have like a log 1 over delta scaling with your query complexity, the final thing will have a log 1 over delta scaling. And otherwise, you would have to pay the error cost of running your base tomography algorithm log 1 over epsilon times.
So, like, do you have any intuition? Because in the way that you're doing it, it seems like if you make a mistake early on, that might cause like bigger problems later. So, how do you get around that kind of idea?
It's actually this is a surprising property of the algorithm that's not obvious from this, but more or less what's happening is that you're still doing this like sort of 1 bit at a time kind of approximation. So if you mess up on a particular iteration, then the subsequent iterations are not going to perturb you too much. So if you mess up on the kth iteration, you already knew that your error was like 1 over k, and it actually won't get worse from there. So your error degrades gracefully, I guess, in that sense.
Thank you.
Great talk, thank you. I was wondering if there, like following up on the experimental motivation of this idea, is there any hope of generalizing these techniques to comparing to the in-diamond norm to a quantum channel?
You're talking about generalizing to quantum channels?
Right.
So with quantum channels, you run into an issue where if you like sort of like, for example, if you apply it repeatedly, you're like losing information rather than sort of maintaining the same amount of information.
Right. Exactly.
If you're close to unitary, then these approaches will probably still work. I mean, they won't give Heisenberg type scaling, but they'll give you something that's sort of similar to it. But I actually don't know what the answer is for quantum channels off the top of my head.
Right, right. It seems subtle because of the incoherence. It seems like it'd be very difficult to get something that's Heisenberg limited. But I mean, I think it's an interesting idea to consider a channel that's very close to unitary. Like, under what circumstances you might be able to get Heisenberg limited scaling.
Yeah. Actually, there's like
That's a common situation.
There's a fun like open question I was considering is like if your channel was say with probability half apply one unitary, with probability half apply another unitary. Can you actually learn these unitaries in 1 over epsilon scaling, or do you have to pay 1 over epsilon squared? So I think this would be the sort of thing that you would want to say, apart from just like, okay, like as you go away from unitary, you can still do something. I think this is like somewhat easier to see from our algorithm that this is possible, but it's not clear whether you can get farther than that.
I see. Very interesting.
So my question is more in line with the first one. So could you use something like this technique to do something like a gate set tomography?
So I think gate set tomography and our work is like very similar. Like the set of ideas are very similar. I would say that like probably it's I guess in our setting, what we are able to exploit is the fact that we can sort of extract an estimate and then use this estimate to sort of power up the error. And this is something that I think in gate set tomography, they or like in practical settings, it's not really clear whether you can do it because I'm not sure basically.
Okay, but do you have any intuition on some difference in scalings between the two? Like from gate set tomography that uses randomized benchmarking, maybe.
Sorry, like the.
Do you have any intuition how this method compare with randomized benchmarking, for example, when you do gate set tomography or something?
I think there's similar algorithms. I guess like I'm not aware of like rigorous provable bounds for gate set tomography, so I'm not really sure if there's a comparison there.
Thank you.
Okay, we have time for one short question, but please feel free to switch rooms if you have to, because it's about time.
Yeah, so you, in your model, you don't have access to the inverse or to the controlled versions, but you still get this Heisenberg scaling, which is kind of surprising. Is it possible, like, so does the lower bound hold even in these stronger axis models? Or,
yes.
okay.
Yes. Yeah. So the lower bound holds in like a very strong model. Yeah.
All right. Let's thank Even again.